to the functions 11 class by doing something magnificent to detect the breast cancers using the neural networks, just using the functions that we learned in the functions 11 course. It's going to be a wonderful experiment. Okay, now we just want to move on to the course. But before that, before I just move on to the course, to do some kind of analytical stuff, I'm just going to go to the Desmos to show you a function that essentially you can think of it as the things that we did yesterday. Guys, everyone, do you see the shared screen on the Desmos?
Yes, we can see it.
Yes. I'm just going to start to develop a function as a transformation of the single variable, which I'm just going to represent it as an x. And I say that function, it's becoming a polynomial functions of the second degree that we call that, for fun, quadratic functions. This function comes with the leading coefficients of 1 minus 4x minus 1. This is going to be the functions that you see. You saw that from yesterday. If I simply leading coefficients becomes minus, the functions becomes upside down, but we do not want to do that. We see that function there. I plotted this function. It's x squared minus 4x minus 1. That's the functions that we just want to just work with it. Okay. Let me six. Okay. 4. Okay. Guys, look at this function. I changed the function to x squared minus 4x plus 3. Look at the functions which I have. We have the intercepts. That's the quadratic functions of the leading coefficients plus 1. Look at this function which is plotted here. We see that we have the intercepts, two intercepts with the x-axis, which they happen to be the points, I should say, x equal to 1 and x equal to, let's say, 3. And also, you see that there is also one y-intercept, which it happens to be at point number 3. And you see also, there is a point, this is 2 minus 1, which is going to be, I should say, at the minimum of the functions. That's, we see that if you look at the functions, imagine that you are rolling over, for example, the functions from top to down. When you reach to this point, you are coming to the lowest level of the functions. And that's the thing that we just want to do today, to identify these functions that either they are at the lower level of the functions, which we call that the minimum, or they are just going to be at the very top. Look at that. Imagine that's going to be the hill. And for example, you are just want to climb the hill. The hill is modeled as a quadratic functions. Then you see that the point that you reach, it represents the y-axis equal to 7, which happens at the point equals to -2 along the axis. We see that this is going to be the most high value of the functions. Imagine if it's going to be your saving, that you're saving the money. For example, that point is going to be the highest amount of the money that you're having in the bank. Okay, and now, just let me just go back. It's the thing that I just wanted to show that to you before we just go to our whiteboard to start some more analytical stuff. And that's going to be the purpose of the course for today. We are just going to find the point at which the function behaves in a different way. At one point, you see the function is increasing, and I'm just going to explain that to you just in a second. I'm just going to, first of all, write this function, which I had here. We said that the function, we call that it's going to be f of x. It's going to be x squared minus 4x plus 3. That's the functions which we had. Okay, we saw that the functions which we had, when we plotted these functions, I'm going to represent it as the f of x. It's going to be on the y-axis. I'm just going to say x. It's going to be on the x-axis. We said that at 2 points 1 and 3, we have the functions coming all the way there. Okay, we had the functions like this when we plotted it, and we are going to focus today our attention to this point, the point that we call that two different names, vertex, where we can optimize this point to be either the minimum vertex or the maximum vertex. We're going to talk about this. We are just going to talk about the strategy that we find these points in any, I should say, in any polynomial functions, not only the quadratic function. But before we just start doing the math behind those stuff that we want to do, imagine that you are going to some kind of a discovery trip. You are just walking along the x-axis and you're walking towards that direction. At any point that you go, you see that when you are getting closer to the functions along the x-axis, which you go from the minus infinity to the plus infinity, you see that when you are getting close to this function, the values that you can read as you move on along the x is reducing. Look at that. For example, at this point, when you look at the functions as here, when you are here, for example, when you are here, you see the function, it reads to that point. When you are here, you see the function reads to that point. When you move along the x-axis, you move to here, you see the function becomes 0. When you go, for example, here, you here becomes 0. When you are here, you see the functions becomes even minus. When you come here, you see the function is getting lower and lower until you reach to this point, which is at the very bottom of, I should say, that quadratic functions. You see that at this point, the function gives you this, let me put that with this color. You see that at this point, the functions that you read is going to be this. It reads a value for you, that the value that you read from this one, we call that, let's say, if that function, it's going to be, let's say, we call that x. I call that xc. I'm going to explain to you just in a second what do I mean by the xc. We get here to be what? To get something as, we can call that f of x of c. Because this is going to be the functions f of x. Then if you have, let's say, xc, on this point, you get the corresponding value of the f of xc on the y-axis. Then I call that c, but the interesting thing which happens after that is going to be this. You see that after this point, any points that you pick up along the curve of these functions, you see that the value of the y from this, the lowest one, it's getting again reversing its trend. It gets higher and higher. You come, for example, here, you see that when you get here, you read this value along, for example, along the y-axis. For example, you call that point, for example, you call this point, you call that, for example, x a. You see that f of x a is going to get higher. You see, we saw a very interesting trend for this function. Initially, the function was decreasing, then suddenly at this point, it changes its behavior. From decreasing, it changes, it reverses its behavior. It becomes, it is growing now. Individually, it's growing. Now, we are just going to put more formalized stuff into finding the functions, finding these points, that it becomes not only the minimum level of the functions, but also at these points, the function behavior changes suddenly. Now, in order to develop this formula, the method which I'm just going to use, it's not going to be only for the quadratic functions. The thing which you have in the book is just for the quadratic functions. The method that we use, you can use it also with the functions which they are cubic, or the polynomials which they have the degree of the 4. Now, then we are interested at this stage to formally understand these points, the points that the functions, they changes their behavior suddenly. Okay, now, what's going to be done then? How can we just follow, how can we just find these points of points that they are critical? In order to do that, I'm just going to go to, let's say, for example, the next page, and I'm just going to develop just a part of the functions. I'm not going to show the all functions to you. I'm going to only show just a very simple part of the function, which you can think of it like that. Just, it's going to be a very tiny part of the functions. This part can belong to a quadratic, to a cubic, to even a polynomial of degree 10. What I'm going to do, first of all, I come here and say that, okay, I have a point here. For example, I call this point x of a. And you see that if you have a point there, you can very easily find its corresponding value on the y-axis. We call that what? We call that f of x a. If we assume that the functions that we have, it's denoted as a single variable functions. The other thing which I do, I just come here to do what? I pick up another point. I get this point, and I say that the point which I'm just going to pick up, it can be any points, it doesn't matter. I'm going to call that x of b. It was x of a here, it's going to be x of b. And equivalently, I can find its corresponding value on the y-axis, which is going to be what? F of xb. So far, so good, huh? We haven't done something crazy yet, except that we just had a magnifier or a microscope. We focus on one single stretch of the functions f of x. With these 2 points, which represents 2 points along the curve. You have seen that before, that you can just come here and connect these 2 points together. You can come here, connect these 2 points together, and you say that this is a straight line. And when you are working with the straight line, you know that the equation of a straight line can be represented like y equals to ax plus b. right? You have seen that before, huh? Yes, everyone? Anybody who hasn't seen that before? Straight line equation?
Yes.
You have seen it. Nice. And now look at this. We have two things which is very important. And you cannot even believe that. Even if you just go to a PhD program, you are doing some modeling techniques which you still use the same functions. They call that regression analysis, linear regression analysis. All the problems that you have, it's going to be about the value of the A. You say, I'm just going to call A. I'm going to call that slope, which it also, as you will see that in the next year, they call that average rate of return. You have seen that you can find the average rate of return. You say that in order to find the average rate of return, I have a very easy thing to do. The easy thing which I can do, and I have it just right in front of me, in order to find the slope, is going to be very easy. I come here and say f of xb minus f of xa divided by xb minus xa. It is going to essentially represent the slope of the line that I'm interested to connect these 2 points together. And you know that also, in order to find the value of the b, even it's going to be much easier. You have the slope, you pick one of the points, either a or b, you plug it in those equations for y, b, and for example, xb, then you turn out the problem into one single algebraic equation. It takes maybe 2 seconds sometimes to solve these equations, as long as you have defined A. A is a very important thing. Now, we call this one slope, or sometimes we call that average rate of change. Right? That's what we call that. Now, I'm coming to the next page, and I'm just going to practice something different right now with you. And I say, okay, what I'm going to do, I'm just going to come here again to represent the same part of the graph that we just put the microscope on, f of x that we had before. We come here again, we pick up this point, which is going to be point A, and I just drop it there. I can see that, okay, very easily, I can see that it's going to be XA. And also very easily, I can say that this one is going to be the value of f of XA. Guys, however, we are always sometimes lazy. In the math, there is a principle which is called Parsimony Principle, which it means that whatever you want to do, you always stick by to do it in a simpler way. If you want to drive a model, you pick up a model which represents your reality, but with simpler, I should say, assumptions. I'm going to do this one again here. Instead of I come here to say that, for example, the point B, which I did before, it becomes, instead of I just call that x of b, I'm not going to do this. I'm just going to come here simply to say that in order to find the points, I'm going to be very lazy. I'm going to target the points. I'm just going to create, for example, the distance from where I'm standing. And I call that distance, let me call that h. In some books, you see that delta x, which it shows that the variation of the delta x. I'll leave that notation for you on the upper years when you go to do the calculus class. Then here we say that the h is going to be the distance that you take from the point that right now you are standing to the point that you target to be. Then this point, which I plan to find myself there, I'm just going to call this simply XA, where I was standing before, plus the distance which I have to take myself there, XA plus H. You see, instead of writing it there as XB, I write it XA plus H. Then you see that you have the complete freedom how far you want to move. You can say, okay, H can be 1 meter, I end up here, H can be 2 meters, H can be any meters, or H can be minus 1 meter. Then it means that you are moving backwards. You, for example, find yourself here. For example, it's going to be XA minus H. But we do not need to just work with this one. The backward movements, I do not do this. You can also think of it in that way, but we focus on the forward movements. It means that we just look at forward direction. If that's going to be the case, then you will see that also here. I can come here and say the value of my functions at point B becomes f of XA plus H. Does it make sense so far? Everyone is fine?
Yeah, it's okay.
That's right. And now, in order again, imagine that I can again come here to find the same, I should say, the same line, straight line between these two things. Sometimes we call this line secant line. However, I'm not going to go to this terminology. I leave it for you on the upper years. Again, the thing that I know that the line AB, if I can call it, this is a line which is represented by another simple formula, y equals ax plus b. There is no difference at all. Again, the straight line equation is something very universal and there is no change. The problem is that here, I again come to ask myself, between these 2 points, what is going to be the value of A, which is going to be the slope of the secant line, or what sometimes we call that average rate of return. If I find A, it means that I can very easily find the value of slope, which essentially you can come up to the equation of a straight line which connects these 2 points. For this case, the same thing. The principle is the same thing. I say the variation along the x-axis, which is going to be f of xa plus h minus f of xa divided by what? Divided by, right now look at this, it is going to be very interesting. We keep the same consistency of the orders of the points that I'm interested for. If I started with the value of f of xa plus h, then I know that I have to be consistent. I write xa plus h minus the xa itself. That's the thing which we have seen that a couple of years ago, and we have no problem with it. But look at this. I have xa here at the denominator, and I have minus xa there. It means that I can simply, without any trouble, come here and simplify my equation, and I said that the slope, or the average rate of the change which I have for this equation, it's simply because what becomes very easy. It simply becomes, it is reduced to this formula. Then it becomes f of xa plus h minus f of xa divided by h. This one essentially, the thing which I derived here, it is the slope and rate of change of these 2 points which I have along the curve. Everyone is good so far? No questions? Now, what's going to happen now? Guys, if I want to go back to the, the whole picture, the global picture of the quadratic functions or polynomial second degree which we had, you see that, for example, the points which we have there, this point, things always happens too suddenly. For example, at this point that the function is decreasing, it suddenly changes to become increasing. You can think of it as the changes of the weather. For example, in the spring here in Toronto, when this is a spring, you see the weather is totally sunny and it's warm, it's pleasant, just within a single second that you didn't expect it. You do not have the umbrella with yourself to go outside, you see that the weather starts to rain. The change doesn't happen from the sunny weather to the rainy weather. The change doesn't happen, let's say, in 2 hours. For example, you do not see the cloud starts to cover the sky, the color becomes darker and darker, the first drop of the rain starts to come after 10 minutes, another drop comes off. It's not going to be gradual change. The change of the weather, it's too sudden. It happens all at the same time. And also the same thing happens like this. Imagine, for example, the function when it is decreasing. I show that by this unhappy face. When the function starts to get increased, suddenly right here, it becomes decreasing so sudden. Sorry, no, it's gonna be, I should say, a happy face now. You see, things happen too sudden, and all those things happens just around this point, 1 point. Then it means that the changes that you are interested to find in our function, it happens just at the close vicinity or the neighborhood of that point. For example, it all should happen at the close neighborhood of that point. You see, I connect these points, the neighborhood, the close vicinity, at a symmetric around the point, in case if you want to move backwards. But you see that the distance, which you can define it by the h again, it's too small. Does it make sense to everyone?
Yes.
We are looking at the changes around the point xa at the very close neighborhood. It seems that, for example, imagine here that, for example, you have point xa is going to be your house. At the point xa plus h is a restaurant. You want to go out to eat, but you do not want to drive for 2 hours to just get to a restaurant to eat. You want to go downstairs, grab a food, come back upstairs. And that's what it means. Then if it's going to be like that, we see that here we have a tendency that the h, which it shows the distance that you take to go to grab your food, it becomes very small. It becomes incredibly small. Then that's why we say that in math, we show that h is going to be close to 0. We have two notations. I could have written h should be equal to 0, but I didn't write it in that way. Because it doesn't mean that the h is going to be 0 exactly. It means that the h is getting close to 0. It means that, for example, it's so close to 0, but it's not 0. That's the notation that we do this in the math. Everyone is okay so far?
Yeah.
Great. Then you see that when you come to find the slope, let me go to the next line. Going to the next, I should say, these ones here. And I'm just going to show the same thing again. For example, this is going to be the functions that we talked, f of x. It was the point A, which we dropped it here to the point XA. And we assume that the XA, which I'm just going to take, is going to be so close to this one. Then you see that, for example, I'm just going to come H to be at this distance. Then you see that, for example, the point X, the point which we call that XA plus H, as H is too small, the point B is going to be so close to A. You see that? Then you see that when you come to drop the line between these 2 points, you see the line is so close to the point A, and they call that the tangent line. Don't go into too much of the terminologies. We see that the line now which connects them, it becomes a little bit different. Again, we have the same thing, y equals to ax plus b. And as I drive that before for you, we said that a as the slope of that line it simply becomes this equation, that it becomes f of x. I had xa plus h. I can simply call this x, that because a is a dummy index, you can change it to b or anything, but I'm just going to remove it to generalize the idea that we are just moving to, and I say f of x plus h minus f of x you see that that's the same thing I'm following, but this is going to be these 2 points divided by what? Divided by h. We had it before, right? And we say that we had these things on our mind, that because we are looking for sudden changes at around the point, we say that critically h is getting close to 0. That's right. So far, accept this formula from me. That's going to be the formula. We are going to love it a lot. That's why I surround it with the heart signs. I'm going to add symbol notations to that at the end of the lectures in order to show the completeness of my representation. But without that symbol, we can just still continue, because that symbol is going to be the course which you're going to take to the calculus class. I'm not going to get into this at this stage. Okay, but this one so far, A represents the slope of this line, which you have created. A is going to be the slope of this line, which I created it. And I'm not working towards B. B is not that important at this stage for me. This A is the slope of a tangent line, which I call the line between A and B. Then H goes to 0. It means getting close to 0. Okay, now, I'm not going to just go back to the real life, and I'm just going to represent the function which I initially showed that to you on the Desmos. What was the functions that we worked? The functions that we worked was this: f of x was equal to x squared minus 4x plus 3, correct? This one was this. I'm just going to do what? I'm just going to come here. Imagine that the plot that I have here, it's going to be that function, which is x squared minus 4x plus 3. It can take any formats, but we are just going to go ahead and as an example to just do this one. What I'm going to do, I'm just going to come here to write A, the slope of the change. the slope of the tangent line or the average rate of change. In that case, they call that instantaneous, but we do not deal. I'm just going to say the names that if you hear them somewhere, you are searching on YouTube, you are searching on Google with the same materials. If you hear these names, you see that, we had similar things in our class. Okay, I'm just going to go ahead and I'm just going to, instead of writing a mysterious function, I'm just going to put the actual value into my function. Guys, if my f of x is this polynomial, if I want to write f of x plus h, what should I do? It means that in the functions which I see, I walk, imagine that it's going to be you are standing on the x. When you put for x plus h, it means that as you move towards the right, wherever you find x, remove the x, put x plus h. Does it make sense? I'm going to do the same thing here. Look at the first term which I have. The first term in my formula here is this, f of x plus h. I'm going to construct the same expression, but with these polynomials which I have. What do? I just start from here. Wherever I see x in polynomial, I put x plus h. It means that for x squared, I write x plus h squared. I continue towards the right. You see, it's me. I continue, I see minus 4. I see x. Then I replace the x with x plus h. I keep moving. I see 3. Does it have any x? No. I write it the way which it is itself. You see? Then as a result, the expression that you see on this side of my bracket, it represents f of x plus h if f is this quadratic function. I move towards the right. Anywhere I saw x, I replace it with x plus h. Any questions, guys?
No.
So far, so good. And the second part of this equation, what is this? The second part of this equation, if you take a look at it, you see the second part of this equation is this expression. F of x itself. F of x itself is normally the same functions that we had. What is the same function? I'm just going to write it with blue to represent this one. It's going to be the same function, the same quadratic function, x squared minus 4x plus 3. You see? And I'm just going to also, I know that it's minus, it's impacting the whole function. Then I make sure that I have these brackets there to show that the minus sign which I have, it belongs to the whole terms of the function, not only for the first, I should say, the leading term. Okay, what is left for me to do? Nothing except I put h, which comes from this formula. You see this h, guys? This is going to be the same h which I put there. Okay, now we are getting to the second step. Now we constructed the formula. Now, what I'm going to do next, I'm just going to simplify the terms which I have. Guys, I think I need only 5 minutes that we can just go for our break. Then I need 5 minutes, please bear with me for 5 minutes, then we just go for our first break then. Sorry, I have only one break with you, first and the last. Okay, look at this one. For this one, I'm just going to expand the first term. But before that, I'm just going to remind you of this thing here. Look at the top right corner. If I have a plus b, I think you have seen that before. We call that an identity. A plus b to the power 2 becomes a squared plus 2 times ab plus b squared. Have you seen this identity?
Yeah.
Okay. If you have seen it, I'm just going to use this identity for the first expression. What does it mean? It means that I'm just going to use it for the first term, x plus h to the power 2. It becomes x squared plus 2 times of x times h plus h squared. Correct? This is going to be this term. This is going to be this term which we have there. I'm going to change the color to write the second term. I have minus 4 times x plus h, which it means that you times minus 4 times x, you get minus 4x. You have minus 4 times h. You have minus 4 times h. Then also, I'm going to change the color to show the 3, which is going to be plus 3. You see? So far, so good, huh? Now, I'm just going to continue with the right side expression. The right expression which I had, what is this? The right expressions which I have is going to be this. I'm going to write it with blue. It's going to be minus x squared. And now minus 4x becomes plus 4x. And I have minus 3 becomes minus 3. And I do not forget, I still have one h at the denominator. Everyone is okay so far? No questions with the second step to simplify the expressions?
Yeah.
Yeah, you mean a question or everything is fine?
No, I mean, it's fine.
Okay. Nice. Now, look at this one. Now, look at that. That's the time to do some housekeeping. The numerator, which I have it here, it's filled with lots of terms, which it needs to be simplified. It means that I just go again, I write my a, the slope of the line between point A and B, and that's going to be the time to do some housekeeping. Guys, look at the first term. I have x squared here. And I have minus x squared here. Similar terms, the opposite sign. It means that you kill them, they are vanished. And I get 0 for it. And also look at this. I have one more term, which they seem similar. Look at minus 4x here and 4x here, plus 4x. You see that? They're also equal times, equal things, but the opposite, I should say, sign, which it means that you kill them. They are gone. They are vanished. And also, what else do I have? I have plus 3. And I have minus 3 here. Again, similar terms, the opposite signs, which means that you kill them. They cannot survive. They are gone. Then what happens here? It means that I have only a few terms which is left. Which it means that, guys, on this example, I'm just gonna, I'm doing it in too slow in order to show the things to you. Do not get bored. On the next exercises, we are gonna make, I should say, we are gonna get some good speed to this. Then I'm just gonna come here and just continue with the other terms. Okay, the terms which is left, I have these terms left. Look at this. I have these terms left. Let me highlight the terms for you. The terms which I have left is gonna be 2xh. I have h squared, and I have minus 4h. Guys, look at that. In all those ones, I have h similar, which it means that you said that you have studied factoring before. It means that you can simply come here, factor h on each term, and write the rest of the terms itself. If you factor h from the first term, what is going to be left? That is, anybody knows? Two x. Is it correct?
Yeah.
Then what is going to be the next term? You said that you studied factoring with Dr. Fraser, huh? You know what's happening here if I write here h? Let me do this in this way that it doesn't get you confused. Let me write the terms which is left. Okay, now guys, look at this. The terms which is left for me from the previous expression, I have 2xh. I have 2xh left from before. I have h squared left, and I have minus 4h. I'm just going to pick up the right colors, which they are on the previous line, that your eyes can see what's going on there. And I had also h at the denominator. You're okay so far, huh?
Yeah.
Okay, now look at this. I'm just going to continue this, put equal, but look at that. On the denominator, at the numerator, which I have, you see that there is a term which is similar to each individual term, which is h. You see the h? I have h, and I have h. It is similar with all terms. It means that I can factor it. I can write h outside, and I say, okay, the rest of the terms should follow after that. What I'm gonna have when I just remove it with 2x? I'm gonna have 2x, because I factored h, which was similar in the term. It means that if you multiply h inside the parentheses, you get 2xh, plus the second term. Look, you're moving towards that direction. The second term, it has h squared. It means that if you take one h from it, which I did it here, I'm left with only one h. And the last term, you have minus 4h. That because you take one h outside first, you are going to be left with 1 minus 4. And I'm going to close the parenthesis. And I know still I have at the denominator h. Guys, does it make sense to you what happened at the second expression than when I factored h?
Yeah.
Is it easy? You said you studied with Dr. Simon, with Dr. Fraser, the factoring, huh?
Yeah, we did it.
Okay. Now, but are you sure? Because you are not so much confident when you say, oh, we did.
No, I just I didn't see x squared and minus x squared, so I was wondering where did the x squared gone? So I didn't say that very confident.
Oh, you mean this one, huh? X squared and
Yeah,
this one, these terms?
I see the minus one, so I was wondering where is x squared?
Oh, you mean on the previous line, huh?
Previous line, yeah.
Oh, did you see these ones? They are highlighted with the same color.
I didn't notice that.
Yellow and yellow. And they are similar with the opposite signs, then they are killed. Are you fine now?
Yeah, now it's good.
Okay. And the terms which I left is 2xh h squared and minus 4x. The terms which I have colors around them, they are vanished with their own colors. Then I factor these ones, then I'm left there. Guys, look at this. Something very interesting is happening right now here. I have h at the denominator, and I have one h which is multiplied at the numerator. That's why we factor them out. Can I simplify them?
Yes.
Yes?
Yeah.
If you say that I can simplify them, I say, okay, if I want to simplify that, I just come here and say, okay, it's going to be like that. My A, which is going to be the slope of the line between point A and B, which are changing so fast, is going to be this h is going to be factored out and cancels out with the h, because one is at the downstairs, the other one is at the upstairs, and they are gone. Then the only thing which is left for me when I do this, I'm going to get with this term which is left inside the parentheses, which is going to be 2x plus h minus 4. Everyone is good?
Yes, sir.
And now look at this one. We previously, I said that to you, I like this term, which I showed that here, that h goes to 0. That was a distance between you that you're living and the restaurants you want to get the food. We said that we do not want to travel so far. We prefer to go downstairs, pick up the food, come upstairs. We are lazy, we don't want to walk so far. And that's what the h goes to 0 means. And I still remember I have to put h still goes to 0. Means h is going to be something very small, very negligible. For example, you have $1 million and someone gives you a penny. A penny compared to $1 million, it's almost nothing, correct? Then
Yeah.
That's what it means. Then at this stage that we are, we know that the h is going to get so close to 0, we can assume that it can be 0 itself. For example, you have $1 million, somebody gives you the penny, then you throw it away. You do not need that. Then it means that at this stage that you are working, we can assume that h is going to be 0. We plug 0 instead of the h. But at the corner of our mind, we know that. We do this. We put h equal to 0, but we know that by principle, h is not 0 itself. It's so close to 0. But in order to make life easy, we close our eyes, we deceive ourselves. We say that. We close our eyes, we deceive ourselves, we put h equal to 0. I mean this equal to 0. Then the thing which we are left with is going to be this, that a, the slope of that line, becomes what? 2x minus 4. Oh my God, I needed more space, but I couldn't do that. A is going to be 2x minus 4. And I'm just going to put everything in, I should say, in the heart, which it's going to be, it means that we love it. I'm only going to write one line before we go for the break, that we start, then we come back from the break to start from this. Then we say that the average rate of change, or the slope of the line AB, is going to be what? Is what it was, 2x minus 4. Am I right? 2x minus 4. Then guys, then I'm just going to stop here, that we can just grab a quick break. Then we see that based on the things that we did, we were able to find the slope of this line, A, which we had also A here, to find the slope of this line. When we come back from the break, we are going to talk about how to start from this A, which we derived from the formula on the top left corner, which is surrounded by the hearts, how to start from this formula, which is simplified, to find the vertex of this quadratic function. Okay, any questions, guys?
No.
I know that we had lots of, I should say, simplifications and new, I should say, concepts, but we are just going to work towards these ones, have more examples, then you understand what's going to happen. I'm going to stop here with this simplified format. When we come back, we are going to talk about, I should say, this behavior of this function. Okay. Now, I'm just going to stop here. The time is 1:12. I think we may need to have 10 minutes, should be fine. But please come back by 1:22. Okay? Please come back by 1:22. 10 minutes break, then we continue from there. Okay?
Okay.
Okay, see you guys in 10 minutes. Talk about that just in a second. Now we go back again to, I should say, to continue with this. Nothing much is left. Then let's see how far we can just go before 2. Okay. Now, what did we did before? We just came here. We just started with, I should say, these quadratic functions, which we had. We used this method. We got to this point, that this point it said that, okay, this is essentially the slope of the line in that quadratic functions that we had. Guys, this one, the thing which we derived here, it has a very interesting interpretation, the A. When you get to the higher levels, let's say, when you take the course which is called Calculus and Vectors, you see that they call this A, they call that the derivative, the first derivative of your function. The process that we did, they call that differentiation. Or when you just go to functions 12, advanced functions 12, you see that they call this one A, instantaneous rate of change. Then you see that you have been able to just move all the videos up there without knowing their terminology, but it's going to be, you see that regardless of what they call that, it has a very important implications for what we are going to do right now. We said that if you imagine that in the quadratic functions that we had, in the quadratic functions which we had, let me change the colors to this one. And we said that if, for example, that's going to be the quadratic functions that these functions which we presented was. The functions which we had, it was f of x, it was x squared, minus 4x plus 3. We see that we were interested at this point because this point, which I'm going to call that xc for 2 reasons. I call the index c for 2 reasons. Why do I call it c? The reason which I have that I call it c is that this point is a crazy point, and C stands for crazy. This point is crazy because up to here, that you get to this point, you are getting so sad because the y function is getting lower and lower. Imagine it's going to be your saving. You are sad. Suddenly, when you get to this point, you suddenly start to laugh. This point is seriously crazy. That's why I call it point xc. C stands for crazy for me, but in terminology in math, they call it C because they call that critical. But I see C stands for crazy. But in the real math, they call that critical. That's why they call it xc. Okay, and that's when it also it becomes f of xc. Now, how to get this one? Because as I said, this point is crazy because it suddenly changes its behavior. But how to find this? What is the value of xc? The value of xc is going to be the root of a. You see that a is, we call that a of x. It's a function of the x because it contains an x itself. You see the x here? That's why I call that a function of the x. Then I say that if I can come here and say that, okay, the root of these functions for x equals to xc becomes 0, it becomes this one. This line tells you that in order to find the x of c, the critical point or the crazy point, you have to take these functions which you got on top equal to 0, which it means that I'm going to take 2x minus 4 goes to 0 or equal to 0. Then you see that to solve this equation, I do not need to just do so much math. I do that 2x equals to 4. Then you see that x equals to 2. That's how you solve this equation. But always remember, put the index c. The index c shows that the point that you discovered there, it's nothing, just a crazy point or a critical point. Then for our example here, the point that we had xc here, it's going to be xc, it becomes plus. No, it just, it becomes, the thing which I draw, it's not the correct one because I had to just put the functions go up. No, that's correct. Sorry, that's correct. It's 2 here. It's plus 2. And this one, it's plus 2. Everything is fine. I got panicked. I don't know why. It's 2. This crazy point or this critical point, whatever you want to call it, it happens at x equal to 2. Then guys, so far, before we finish the session today, you learned a technique in order to find the crazy points of polynomials. You can start with the cubic functions. For example, x cubed plus 2 to the power x2 and goes on. Then by this technique, you are going to find 2 critical points. Then you see that this method is very general to find these critical points. In the textbooks which you have, which is going to be for functions 11, there is another name for this point. Another name which they call this point is, they call that x, they call that, let me write it here, vertex. Then you can say that, okay, it's going to be x of v. It's going to be equal to 2. What is the characteristic of the vertex line? Is this going to be this? That a line, which I'm going to plot it right, let me do that not by dot. Let me change the color and let me draw it as a good line. Okay. I draw a line. The line which I draw here is just parallel to what? It's parallel to the y-axis, and it's passing through the point equal to 2. What is the equation of this line? What is the equation of this line? Parallel to y-axis, and it's passing through the point 2. The equation of this line is x equals to plus 2. Because you see that any points which is along this line, they have the same x value. That's why we define this line as x equal to 2. We can call that x of v equals to 2, but we call that, they call that, that's going to be a vertex line. In the Functions 11 textbook. If you see it in a vertex line, don't be panicked. That's what it means. It means that you find the point, the crazy point, which the way we solve this equation, we find the crazy point, then the point x equals to 2 or anything x equal to xc, it becomes the vertex line. Here we got x equal to 2, the root of this one, then x equal to 2 is the vertex line for this parametric, for this quadratic function. Any questions, guys?
No.
No, everything is fine? Okay, and now I'm just going to stop the share from the whiteboard. I'm just going to go back to the Desmos. In the Desmos, we are going to check that when we plotted this function, did we really get, I should say, x equal to 2 for the point which is going to behave crazy at the lowest level? But before I go, I can also find what is going to be the value of f of x of c. Before I go, let's do that. X of c is going to be 2. What is f of xc? What is the value of the critical point? In order to find the value of the critical point, look at the function there. F of x is this one. Then if you put x equal to 2, you can find f of 2. F of 2 becomes what? Becomes 2 to the power 2 becomes 4 minus 8 plus 3, which equals to what? 7 minus 8 becomes minus 1. Then the critical point which we have, I call that C. It's the point which is x is equals to, I call that x of c equals to 2. And the y of c, it equals to minus 1. This is the critical point here. And this one is coordinate. We got the full coordinates, I mean the x and y of this point who behaves crazy in our quadratic function, or the vertex point of your quadratic function. I'm just going to stop the share, and I'm just going to go back to the Desmos to see that on the plot also itself, we got the same results or not. If the results are going to be different, it means that somewhere we did a mistake, we made a mistake. Let's go back. I'm just going to stop the share from, I should say, the whiteboard. I'm just going to go back to the Desmos, and that's the plot which we did that initially. Okay. Look at this one, guys. The plot which we have. X squared minus 4x plus 3. If you look at this function, you see that the function at this low point, that's the crazy point. The function is decreasing at this stage, then it gets increasing. These points is the point that sudden change happens. We call that point, I should say, critical point. I personally call that a crazy point, and the textbook calls that a vertex point. Look at this point. These points which we draw, based on our calculation, we got these coordinates, x equals to 2 and y it was equal to minus 1. And look at that, we got the same result. Even on the plot, on the Desmos, when you click on that point, you say this, you get the same coordinates. Everybody can see those coordinates, 2 and minus 1?
Yeah.
Yeah, that's nice. Then now we matched the thing which we did analytically with the thing which we just can visualize that on the graph of the function. And if you are wondering what is going to be the vertex line, we saw that the vertex line has the functions equals to x equals to the value of your critical point, which it was 2. You see that? Now I have these points. At x equal to 2, you see that the vertex line, it's plotted at point equal to 2, and you can see the critical point as 2 minus 1 there. And you see that also x equal to 2 is a symmetric line. Because imagine that if the blue plot, the blue line, it becomes a mirror, and you're standing, for example, each side, the left part of the graph is the mirror image of the right, or vice versa. The right is a mirror image of the left one. The distance from each point to the mirror is going to be the equal one. And that's essentially, that's what I wanted to show that to you when we do that on the graph. Okay, let me, this one, that's going to be point 2. And that's going to be a critical point. Okay. Guys, any questions?
No.
No? Okay. Now, before I just stop the lectures here and I give you some examples that you work on it, before we come back tomorrow and we talk about the maximum and the minimum, how to find the maximum and minimum, I just want to finish the lectures today by saying that this one. Guys, the critical points that we got today, based on the method that we got, you can call it a critical point, crazy point, or the vertex point. It is a candidate for a functions to be minimum or maximum. You are finding the lines, the maximum or minimum, they call that optimal points. Tomorrow we are going to talk more about that, but it is a kind of a branch of the science that it has a graduate degrees for it. Some people just go to get the advanced degrees in math, in PhD in math. This is called optimization theories. And the thing which you see is an introduction to optimization theories. That we say that the critical points always happens when we just do this analytical stuff, and the maximum and the minimum value of the function is the critical point. For our case, you see that our critical point also is a minimum point because it is at the low level of the function. You cannot go below that point. The function is not defined lower than point equal to 2 and minus 1. That's what we call that a minimum point. Now, I'm just going to stop the share and go back to the screens that we had, the whiteboard, to finish the lecture of today with 2 interesting things. Tomorrow we go back to talk about that more, but that's going to be what we do today at this stage. Look at this one. For example, the first scenario. I'm going to have a plot. For example, it's going to be the plot of the functions like that. And you can think of this point as a critical point that defined. We know how to find these critical points. I call that x of c. C stands for critical, and it becomes f of x c. And this one itself is f of x, which we saw that the f of x, in our case, is a quadratic functions. A general format can be written as ax squared plus bx plus c. A, b, and c, here they can represent what? They can represent the real number, which they are the coefficients of our polynomials second degree. A, b, and c are real numbers. Okay. Guys, look at that. What can you infer about the sign of the A? because the function opens up, you see that the function is pointing upwards. We talked about that yesterday, that a has to be positive, that the function looks like this. I hope you remember that from the thing that we discussed that yesterday. I'm going to also show you something different. Somehow a similar plot, but the plot is going to look like that. You see that this point is a critical point, which we now have a method to find it. I call that xc. This one is going to be f of xc. And you see that here, the f of x that we have, it can be written in a very general format. Ax squared plus bx plus c. Again, we have the same scenario, a, b, and c. The coefficients has to be necessarily real numbers. In our definition of the polynomials of n degrees or the quadratic functions, which we talked about that yesterday. Based on the things, guys, that we talked about that yesterday, the a slope that we have there, a has to be negative, that the function is opening downside. You see, these are the things that we talked about that yesterday. I didn't introduce any new topic for you right now. These are essentially the topics that we talked about them yesterday. Okay, as a conclusion is that when I'm going to talk about that tomorrow more, you can think of this one. Guys, when I go back to picture number 1, I call that graph number 1. I call this one graph number 2. With the graph number 1, which we have here, the critical point xc, is it the minimum function, is it the minimum value or the maximum value of the plot? I mean, is it at the lowest level of the plot or at the highest level?
Lowest level.
That's so true. That's the lowest level. Then before we move on tomorrow with some calculations, you can derive these conclusions that anytime with the quadratic functions, which its leading coefficients a is positive, the critical value represents the minimum value of the function. Then that's why you can call that point also the minimum value. And xc, it is also the x mean. However, in contrast, we go back to this function, these polynomials, second degree quadratic functions. We see that the a is a leading coefficient is negative. That's why the functions opens down. The critical functions, the critical value which we find, it was this. Now, guys, the critical value which we have, it is at the point that, is it at the toppest level of the graph or at the lower level of the graph?
The top.
That's so true. That's at the very top part of the graph, which it means that we can think of this point also at the same time a maximum point. Then you can have this conclusion for yourself that for a quadratic functions, when the leading coefficient, which is a, is negative, then the critical function also is, the critical value of the x is also the x maximum. Before we move on tomorrow to have some kind of interesting stuff there, that's going to be the thing that we just finish our tutorials for today. Let me write it here. I can write when. Let me change the font. when leading coefficient is positive, then critical point is a minimum point. We call that local minima. You're gonna see that, I should say, in the next lecture. We call that local minima. Contrary for this one, we said that when the leading coefficient, by the leading coefficients I mean A, is negative, then the critical point is a maximum point. They call that local maxima. These are the 2 points I just wanted to draw based on the course that we had today. Okay, any questions, guys?
No.
Nothing? Everything is fine for everyone?
Yes.
Okay. Now, before we leave, I should say, let's spend some time to, I give you one example that you do it on yourself. Okay, I'm gonna give you one example of, as a kind of, it becomes also, you work one part of it for right now, and also you do it as a homework. The homework is gonna be just this one. I'm gonna give you a quadratic function. The quadratic function, which I'm just going to introduce, is going to be f of x. It is essentially, let me give you 1 second, please. Okay, I'm just going to give you only, as I said, 2 options. We said that f of x, I give you 2 ones. One of them is going to be 2x squared plus 12x. And I'm going to also give you this one, the g of x, which is going to be 3x squared minus 6x plus 5. I'm going to call this one as homework. Then the thing which you have to do is that just this one is going to be homework. Please find the critical point and assess the maximum or minimum behavior of those points. That's essentially all the things that we did. You are going to do that as a homework. And please, guys, when you are done on the homework, please take a picture of your homework and send it to me as a text on the Schoology. You go to the Schoology, you can communicate it by sending a message. Send a message to me. Remember, you take a picture of your notes and attach it to your message and send it to me. Okay?
Okay.
And also, before we finish and we leave, guys, I'm just going to remind you again. I'm just going to put the slides, as you saw from yesterday, into a folder which is called July 14. You can get the access to the things which I wrote for you in the class. And also you can get the access to the link to the video of the class that we taught. In case if you have any problems, you can either check the slides, watch the video, or send a text to me to ask your questions. Okay?
Okay.
Awesome. Guys, if you have no questions, we can finish up the session today, and I see you tomorrow then. Any questions from Tom, Allison, Jesse, and Bo?
No.
Now everyone is fine?
Yes.
Yeah, I'm good, sir.
Awesome. Fantastic. Guys, then thanks for today. Have a wonderful evening. Then I see you all tomorrow. Tomorrow, the same hour then.
See you. Have a nice day.
Thank
See you,
you.
sir.
Thanks, Tom. Thanks, Bo. Thanks, Jesse. Thanks, Allison. See you all tomorrow. Take care.
Take care.
Bye-bye.